Okay, so today we're going to tackle a problem in plasticity where we want to look at the moment capacity of a T-beam. So we have the problem laid out. So it says for the T-beam section shown, calculate the elastic moment capacity and curvature, as well as the plastic moment capacity and the curvature plastic. And then we'll do an extra part beyond that where we'll look at somewhere in between. The specifics of that is we're going to calculate the moment if the strain at the web flange interface is equal to the strain of 0.00125, which happens to be the elastic limit to the strain. And then it gives some properties for the cross-section of the material. So I've laid the problem out and gone ahead and looked at the cross section. I figured out what the area was and then what the distance to the centroidal axis is, y bar. And so I've shown those here on the diagram. I've got it laid out. I'm going to largely look at area one being the area of the flange and area 2 being the area of the web. I've identified the distance of the centroidal axis or the neutral axis for the elastic as 90.68 millimeters, and that leaves 44.32 millimeters between the elastic neutral axis and the top of the flange of 44.32 millimeters. So in tackling this problem, what the first thing I want to do is to draw the conditions of the strain and stresses at the point where we reach the elastic capacity of the section. So to get there, I'm going to start by drawing in the strain diagram. And of course, it is always linear and it passes through the neutral axis. And so when we look at the strain diagram, we can see that we're going to have much higher strains in the bottom, so within the web, than we will within the flange. And that's because it's an asymmetric cross-section with more material in the flange carrying load than we have in the web. And so these strains will be, the neutral axis will be in the top half, closer to the top than the bottom, which will give us that asymmetry in the strain diagram. So what do we know? So we know that this condition will occur when we hit our elastic limit. So this strain, strain sub y or epsilon sub y, will occur at sigma y divided by Young's modulus, which is equal to 0.00125. And of course, the curvature of there is going to be equal to this angle in there. So we can determine what the strain at the top of this is just by using similar triangles. So that would be the ratio of the distances from the neutral axis, or 44.32 millimeters, divided by 90.68 millimeters, multiplied by the strain at the bottom, which is 0.00125. And that gives us a value there of 0.000611. So from there, we want to look at the stress diagram. And because we're still within the elastic limit, the stress diagram will also be linear and vary from top to bottom, passing through the neutral axis. And the relationship, of course, because we're elastic, between the stress diagram and the strain diagram is that stress is equal to E strain, or Hooke's law. So typically when we do the stress diagram, we show our stresses as a series of arrows. You can draw them in here. In this case, we're showing compression above the neutral axis and tension below the neutral axis. Now, because of the relationship of Hooke's law and this being epsilon y, then this is also sigma y, or 250 megapascals, which will occur down here. Of course, it occurs at the bottom where the maximum strain is, and by definition, we know that this is the point at which we reach 250 megapascals, or a strain of 0.00125. Again, we can apply similar triangles to figure out what the stress at the top is, or we can just multiply the strain at the top, which we already know, of 0.000611, multiplied by our Young's modulus, 200,000 MPa, to arrive at a stress of 122.19 megapascals. Now, for us to do our calculations to determine what the moment capacity is at this point, I'm just going to redraw the strain diagram, but without all the arrows and everything else in it, so that we can break it up into usable areas for our calculations. So I'm just going to draw it in here. And it doesn't matter at all if it's completely to scale or not. Well, what I need to do now is to break it up into easily usable geometric shapes, but I also have to make sure that each of those shapes has the same width or thickness within the cross section. So that means that I need to have different shapes above and below the flange, as well as this trapezoid we can have as a simple triangle, a rectangle. And so having done that, we have really four shapes, which will make our calculations quite easy when it comes to calculating our elastic moment capacity. So what I need to do is I need to label these shapes. So this is in here, this one will be 1, 2, 3, and 4. And what I want to do is I want to show the centroid of those areas, because that's going to give us our moment arms, and roughly drawing them in and pointing them to there. So our first step in figuring all these things out is to figure out what our distances are to those centroids of those areas 1, 2, 3, and 4. So I'll draw this one over here, and we want to know the distance y1 from the neutral axis, the distance here, y3, the distance y2, and of course down here we have our distance y4. Probably the one distance that I don't have drawn in, which will make this easier, is this distance from the neutral axis to the bottom of the flange. So let me just quickly calculate that as 29.32 millimeters. And that means that I can go y1 is equal to 29.32 millimeters to the bottom of the flange plus 2/3 the height of the flange, or thickness of the flange, which was 15 millimeters, and gives us a y1 value of 39.32 millimeters. Our y2 is equal to that same 29.32 millimeters between the neutral axis and the bottom of the flange, but in this case it's 1/2 the thickness of the flange, 36.82 millimeters. Y3 is equal to 2/3 of the distance between the neutral axis and the bottom of the flange, or 19.35 millimeters. And y4 at the bottom then is 2/3 of y bar, which is 90.68 millimeters, or 60.45 millimeters. So to go with that, what we need to do is to actually calculate what our force components are. And of course, we're going to have a C1, a C2, and a C3 for areas 1, 2, and 3, and a T4 for area 4. And to figure out what the force component is, we take the area of the stress shape and we multiply it through by the thickness over which it acts, so the thickness of the cross section over that area. So we'll just start down here. We'll start with C1. It's a triangle, so its area 1/2 times its stress component, which is 41.35 megapascals, over the height of that triangle being 15 millimeters, or the thickness of the flange, and the width of the cross section on the flange is 100 millimeters. That's equal to 331,013 newtons. C2, it's a rectangle, so its stress component, which is 80.84 megapascals, multiplied by the height over which it acts, which is the thickness of the flange, which is 15 millimeters, and again the width over which it acts, which is the width of the flange, or 100 millimeters, and that's equal to 121,260 newtons. And our final compressive component, or force component, which is the triangle 3. So a triangle be 1/2 the height, or its stress component, 8.84 megapascals. The height of the triangle over which it acts is the 29.32 millimeters, and the thickness of the component, which is the thickness of the web, which is 15 millimeters, and that's equal to 17,776 newtons. And over here we'll do T4, and T4, again a triangle, so 1/2 times its stress component, so we know that it's at 250 megapascals in here, multiplied by the height of the triangle, which is y bar, or 90.68 millimeters, and the thickness, or the width over which the cross-section over the area which it acts, which is the width of the flange, or 15 millimeters, and that then is equal to 170,025 newtons. So as a quick check, so we basically have 170 kilonewtons there, and if we were to add that up, we basically get 170 kilonewtons there. So some of the forces in the Z direction equal in compression and tension. So to get the moment capacity at this condition, then basically we have to do the sum of the moments about the neutral axis. And so doing them in order, 1, 2, 3, and 4, we take its force, in this case 31,000 newtons, multiplied by its moment arm, which would be y1, which we calculated earlier to be 39.32 millimeters. And we carry on, we do that for each of C2, C3, and T4. So 121,260 newtons multiplied by y2, 36.82 millimeters, plus C3, which is 17,776 newtons, times Y3 of 19.35 millimeters, plus T4, which is 170,025 newtons, times 60.45 millimeters. When we run that through our calculator, we get 16,301,873 Newton millimeters, or 16.3 kilonewton meters. And we'll just highlight that. And the curvature that goes with it. So our curvature elastic is equal to our strain elastic, so 0.00125 divided by the distance that it took to get there. So that's 0.00125, which occurs at the bottom of the cross section, and y bar divided by y bar, which is the distance between the neutral axis and where that strain occurs, or 90.68 millimeters. So that strain, that distance, and that gives us a curvature of 1.4 times 10 to the negative 5 millimeters to the negative 1. So that's the first part of the question. So we have our moment capacity elastic and our curvature associated with it. Now what we want to do is basically do the same problem again, only in this case we're going to draw it out for the point at which the entire cross section is in a plastic condition. So I'm just going to scroll down my page, set up the diagram, or get ready to set up the diagram for the plastic moment capacity. So there we go. I've set up the page, and I'm going to go through a very, very similar process to what we did before. It gets a little bit simplified, actually, because of the cross-section being fully plastic. So again, I'm going to start off in the same way we did before, and I'm going to draw my strain diagram. There we go. Pretty close anyway. Passing through the neutral axis, equal to 0. Close that. Top and bottom. And we're going to have our strain at rupture 0.2. So considerably higher order of magnitude than before. And of course, it will arrive at that rupture strain at the bottom because the neutral axis is considerably higher. Now, one of the things to be aware of course, is I've erased the dimensions that we had because the neutral axis, although I didn't bother to show it having shifted, it will actually occur at a different location than it did during the elastic capacity, and that's because the cross-section itself is asymmetric. So because of the large flange, when the web starts to go into plasticity, the flange is still elastic, and so the neutral axis, to maintain the compressive force and the tensile force being equal, will have to start to shift and move around. And one of the things we're going to have to do when we calculate this is to figure out what is the position of the plastic neutral axis and figure that out. So if that's our strain diagram, then I'm going to do the stress diagram right beside it. I'll try to not using any particular scale, but in this case, because the entire cross section is plastic, we don't have that Hooke's law relationship between stress and strain anymore. That only occurs during the elastic portion. And so the entire cross section will be at sigma y. And again, we'll draw in our little arrows. I'm going to draw it out again without the arrows and everything, just so we can break it up into those simple shapes that allow us to calculate the moment capacity. I'll put in the actual values for our strains and our simple areas in this case. So we're going to again have to break it at the where the flange and the web meet because the thicknesses are different. And so we're going to have area 1, area 2, area 3. And if I were to anticipate, I'll put the centroids. They'll happen in the middle, right there. And Y2, Y1, and Y3. So the first thing we need to do is we're going to have to figure out where the neutral axis occurs at this point of rupture. And the one thing that we know is that because it's all at 250 megapascals, there's no elastic component in there, that when we do the sum of the forces in the z direction equals 0, therefore C must be equal to T. C is equal to the area in compression multiplied by sigma y, and T is equal to the area in tension multiplied by sigma y. So if C must be equal to T and the y's can cancel out, therefore area of compression must be equal to the area in tension, which is equal to the total area divided by 2, which in our case, we had our area, it was just off the screen here, 3,300 millimeters squared divided by 2, which is equal to 1650 millimeters squared. So with that done, we can then figure out what the height to the neutral axis is. So Y bar plastic, because the area in tension, which is equal to 1650 millimeters squared, which is equal to the thickness or the width of the web, which is 15 millimeters, multiplied by Y bar plastic. And so we can determine that Y bar plastic is equal to 110 millimeters. And I'll draw that in there. So with that known, it's worth our time to put in a couple of the other dimensions. So we can figure out that if this is 15 millimeters, that leaves us with this as 10 millimeters. We can fairly quickly deduce that 110 divided by 2, so Y3 is equal to 55 millimeters. Y2 is equal to 5 millimeters. And y1 is that 5 millimeters plus half of 15, or 17.5 millimeters. And I'll just do them out quickly there just to save ourselves a little bit of time. So a good intermediary step to getting the plastic moment capacity is to figure out the, the plastic section modulus, or Z. So we know that Z, or the plastic section modulus, is equal to the sum of the areas multiplied by their moment arm from the neutral axis. And so we'll go 1, 2, and then 3. So the area 1 is 100 millimeters wide times 15 millimeters in height, multiplied by y1, which was 17.5 millimeters. So area 2, we have our flange width of 15 millimeters, plus our height, which is 10 millimeters between the neutral axis and the bottom of the flange, and y2, which is 5 millimeters. And to that, we have to add area 3, which has our flange width of 15 millimeters, and Y bar plastic, which is 110 millimeters, and Y3, which is 55 millimeters. So we can run those through our calculator. We get a section modulus of 117,750 millimeters cubed. And that was useful because we know that our M sub P is equal to our plastic section modulus times our yield stress, which is equal to 117,750 millimeters cubed times 250 megapascals, or 29,437,500 Newton millimeters, or 29.44 kilonewton meters. And before we go too far, we want to figure out what our curvature plastic is. And so we do that same ratio that we did before. So we have to, in this case, use our rupture strain and the distance from the neutral axis associated with that, which is 110 millimeters. So we have Y bar plastic 0.2 divided by 110 millimeters, or 0.001818 millimeters to the -1. So that's the elastic condition and the plastic condition. We've got the capacity M sub Y and M sub P for the plastic condition, and the curvature is related to each of those. And then the final part of the question, which was to look at some point between those two conditions where a portion of the beam is still elastic and the remainder of the beam is in a plastic condition. And so what it says is to calculate the capacity of the cross section, the moment capacity of the cross section, when the strain at the flange web interface is equal to the elastic strain, so 0.00125. Sorry, and we'll put that in compression. So this is useful to us in one way because we know that everything above that, so everything in the flange will be plastic, and a portion of the web will be elastic from the bottom of the flange down to the plastic neutral axis, and then from the plastic neutral axis down, there will be a portion that is elastic and a portion that is plastic. The portions of the beam in this case that are elastic are symmetric, which is critical to one assumption that we want to make in order to facilitate this calculation, which is that the neutral axis will not move or will remain at the plastic neutral axis as we relieve some of the moment between there. If the elastic portion were to go into the flange itself, the asymmetry would be engaged and the neutral axis would start to vary between the elastic neutral axis and the plastic neutral axis, which would make the question somewhat complicated. So this makes it much more achievable, because what we're able to do is to say, assume, and we can demonstrate it later if we like, that y bar elastic plastic, so the location of the neutral axis for this condition, is equal to y bar plastic. And it's a good assumption. So let me just set up for my diagrams. We've got to do this one more time. We should be able to go through it fairly quickly and determine what the capacity is in this case. Okay, so we've got our positions all sorted out. So a couple things. So we know that y bar plastic is, so we're still keeping the neutral axis in the same spot. So that's equal to 110 millimeters, which means that this is still 10 and this is 15. Thus, these distances here, so this is still 17.5. I'm just transferring these down from before. So we don't have to recalculate them because they're all the same. And this is equal to 55. So that'll help us speed things up just a little bit. So like before, the first thing I want to do is draw in my strain distribution. It stays linear, as it does in all cases here. And the difference here is that we know that this strain in here is equal to negative 0.00125. And at an equal distance from the plastic neutral axis, it will be equal to positive 0.00125. And we don't necessarily know what the strains are at the extreme fiber. They would be something less than the rupture strain down here, because we know we're less than the plastic moment. So if we were to draw in our stress diagram, so we have the flange, which is plastic, and then it is elastic through the neutral axis to the same distance below. We were to draw these in, so this is what the stress distribution is going to look like. Is we're going to have a portion of the beam, top and bottom, which are plastic, and so they have achieved sigma y equals 250 megapascals. And then some portion which is elastic, and for that portion, of course, Hooke's law, stress equals E strain, would apply just between those parts that have gone plastic. So like I did before, I'm going to just very quickly draw out, I'll probably stretch the scale a little bit so we can see our shapes. And then I will label my areas. So 1, 2, which will be in compression, 3 and 4, which are going to be in tension. And I'll draw in I'll put dots for my centroids again. And we already have marked this y1, y2, y3, and y4. So y1 is equal to our 10 millimeters between the neutral axis and the bottom of the flange, plus half the thickness of the flange, or 1/2 times 15 millimeters. That's equal to 17.5 millimeters. Y2 would be 2/3 of our distance between the neutral axis and the bottom of the flange, or 10 millimeters, which would be equal to 6.67 millimeters. Y3 has to be that same distance because the distance down the strain diagram where we transition between elasticity and plasticity has to be the same distance as it is going above the neutral axis. So and then y4 would be equal to that distance down to that transition, or 10 millimeters, plus 1/2 of the remaining 100 millimeters, or 60 millimeters. So as before, we're going to go ahead and calculate our force components. So C1 is equal to our stress component. It's in plasticity, so 250 MPa times, and I may as well probably draw that in or show that here. So that's 250 MPa, 250 MPa times 100 millimeters times 15 millimeters for the thickness of the flange, and that's equal to 375 times 10 to the third newtons. C2 then is that triangular shape, so the maximum intensity of the stress is 250 MPa. Height of the triangle we know was 10 millimeters, and thickness of the flange is 15 millimeters. So that's equal to 18.75 times 10 to the third newtons. And T3, again, we have a triangle. Maximum stress component is 250 MPa. It's 10 millimeters down along the flange, and 15, or down along the web, pardon me, and 15 millimeters width of the web. That's equal to 18.75 times 10 to the third newtons. Finally, T4, 250 MPa stress component times the 100 millimeters times the width of the web of 15 millimeters, equal to 375 times 10 to the third newtons. So easy to see that if we were to add those up, that they're equal. 393.75, and tension 393.75 in compression. So to get the capacity at this point, or at this condition of loading, so we do the sum of the moments about the neutral axis is equal to our force components for each of those areas. So 375 times 10 to the third newtons for one, times its moment arm, which in this case is y1, or 17.5 millimeters, plus C2, which is 18.75 times 10 to the third, times its moment arm of 6.67 millimeters, plus T3, which is 18.75 times 10 to the third newtons. So I missed a newtons back there. Gotta do that. Multiplied by its moment arm of 6.67 millimeters. And finally, we add in T4, which is 375 times 10 to the third newtons times its moment arm of 60 millimeters, which, so when we run that all through our calculator, we get 29.3 times 10 to the 6th Newton millimeters, which is 29.3 kilonewton meters. And it's worth noting that that is almost the same as the plastic moment, because we haven't actually shifted that much of the material of the cross section back into the elastic range. It's actually the vast majority of this cross section is at its plastic capacity, and so we've only reduced the moment ever so slightly, with only 10 millimeters either side of the neutral axis, which is carrying load elastically. So that's it. We have three conditions. We started with the elastic condition to get the elastic capacity of the cross section. We did the plastic capacity of the cross section, and we did some condition in between at a specific strain condition. So I hope that was useful to you, helped to understand a little bit more about the mechanics of the cross-section and the relationship between the strain and the stress diagrams as we transition between elasticity and plasticity in the cross-section. So hopefully that was useful to you, and we'll see you at the next time.